I'm Caroline Dorn, and as part of this collaboration between the University of Bern and ETH Zurich, I'm studying what we can learn about the interior structure of rocky exoplanets by their measured mass and radius only. And what you see in the background of this image is the Cheops satellite. This is an upcoming mission of ESA, where the leading house is Bern. This mission is to characterize exoplanets, and my project is part of the science of Cheops. The search for exoplanets started booming with the first discovery in 1995 by Meyer and Queloz. And this discovery was very interesting in itself because this was a hot Jupiter, so a planet of a new class of planets that we don't have in our solar system. And over the past 20 years, there was extraordinary progress in the detection of new exoplanets, thanks to a long list of ground-based and space-based missions, especially the Kepler mission. And today we have almost 2,000 exoplanets known. So we learned exoplanets are common. They are as many planets as there are stars, if not more. And these exoplanets seem to have a very wide range of properties compared to our solar system. And so the question arises, how are these planets or these planet types distributed among stars? Is our solar system common or not? And is the Earth a common planet or not? So these are the driving questions of the community. And when I plot the discovered planets depending on their distance to the star versus mass, you will see that we mainly picked up planets very close to their stars and with very high masses. And due to this color coding, you also see that depending on the detection method that is used, we are sensitive to planets of certain properties. And I will briefly introduce you to the two main detection methods. That is the radial velocity method and the transit method. So with the transit method, you can derive the radius of the star by the dip in brightness when the planet sits in front of the star. And the radial velocity method yields the mass of these planets. So due to this gravitational interaction between a massive planet and its star, the star has a radial velocity, it wobbles around, and this can be measured through the Doppler shift. Of course, both methods have their biases. They are biased towards large planets or massive planets close to their stars. Well, the combination of both methods provides further access to the mean density of these planets, which is the first step to characterize their interior types. And if you see here the planets where we have actually radius and mass measurements, they plot here on a continuum of radii and masses. I also plotted some iso density lines of Earth, Neptune, and Saturn. And you see we find these planets on a continuum of densities. So what are these exoplanets actually made of? Given that we find them on a continuum of densities, we can imagine having a very diverse range of interior types that we don't find in our solar system. We can imagine having super Earths or these gas dwarfs or subgiants with massive cores. So previous work on this to answer this question was done in the following way, that they studied how a specific interior structure and composition scales with radius and mass. And to determine then an interior structure of an exoplanet, you can simply plot measured mass and radius and plot this against some specific mass radius curves of specific interior structures. But the weakness of this approach is that it doesn't account for the inherent degeneracy, the ambiguity there is that very different interior models can have identical mass and radius. And so, due to this inherent degeneracy, the analysis or the determination of all the possible interior models can only be done sensibly using Bayesian inference. And we are using an inverse approach which enables us then to study all the range of possible interior models that fit the data of mass and radius. And in this study, we restrict ourselves to purely rocky exoplanets, where we say that oceans or atmospheres have a negligible effect on mass and radius. And so let's see what we can constrain by just having mass and radius. The model assumptions that we are using are the following. We have a mantle that is comprised of all these oxides, where the oxides of iron, magnesium, and silicon are the main oxides in the mantle. We have an adiabatic temperature profile in the mantle similar to the Earth. The core is made of pure iron, and we also have an adiabatic temperature profile. The model parameters that we want to constrain are these four, the first three for the mantle composition, and the fourth is the core radius. And so for any given choice of these model parameters, we can then calculate the mass and the radius through this G of M, which maps a model into the data space. And for this G of M, we are using for the mantle a thermodynamic modeling developed by James Connolly, the purple X, and for the core, we are using equation of states for pure iron. And so, given this G of M, or this forward physical model, we can calculate these density profiles and then integrate to get mass and radius. So to calculate now the posterior of these four model parameters that we want to constrain, we need to define prior and data. And the prior that we are using for this case A now is a very wide prior, a very conservative prior, and the data is simply mass and radius. And on this mass-radius plot, you see that we find solutions that are indicated here by the filled cycles that are all sitting between the pure iron and the pure silicate sphere, which we expect to happen. Now, every dot in here represents an inverse problem that has been solved, and I will show you what happens when we apply our method to the Earth case. In the first figure here, you see 4 panels for every model parameter. So the first 3 for the mantle composition and the core radius in the last one. In red is the prior, in blue the posterior, and in green are some independent estimates. And you see that the prior and the posterior are not so different for the mantle composition. So these can't be constrained. The core radius is somewhat constrained, and we see there's a very weak correlation. So these plots are showing the correlation between the model parameters, and the correlation is generally weak. So the only parameters that we can constrain by mass and radius is actually the core radius. So this doesn't look too good, but can we do better on this? Well, there are arguments from planet formation studies that are studying the chemistry or the compositions of planets that are formed in circumstellar disks, when they also couple this with chemical equilibrium calculations, and they succeed of correlating the bulk chemical composition of the planets that are formed with the composition, the chemistry of the host star. through elemental ratios, actually. And this is the case for these elemental ratios, iron to silicon and magnesium to silicon. And they find for these two ratios a one-to-one relation between the one of the star to the planets that are formed in these disks, which is good news for us because our planets are mainly made of these elements. And in addition, these elemental ratios can be measured from the photosphere of the stars. So what we can do now is we add these abundance constraints to our inversion, and these enter in the prior as well as in the data. And when we look on the mass radius plots, we see that where we find solutions, we find them in a reduced region where we can still met the abundance constraint that we have from the host star. And here I show you solar abundance constraints. And what happens now to the Earth case when we have these added elemental abundance constraints? In the first figure, as before, I show you the four model parameters. And now we see, first of all, the prior range is significantly smaller than before, mainly here. The correlation between the model parameters is much stronger. This means that we have now a strong correlation also between the core and the mental composition, which is why we start to constrain also now the mental composition. And our posteriors predict well the independent estimates. For the core radius, we see that we under-predict the core radius. This is due to the fact that we assume pure iron for the core, so we overestimate the density in the core. So what happens now if we apply this method to exoplanets? Here I show you all the planets that are detected in the mass radius range of interest. Unfortunately, we don't have photospheric abundance ratios measured or published from these host star. So now I simply assume solar abundances for the moment. And I will show you what happens when we apply our method to Kepler 36b that has the smallest uncertainty ranges on mass and radius. And here I show you this case A, where we only assume mass and radius as the data, as well as case B, where we add these solar abundance values. And we see in case A, again, the only parameters that we can constrain is the core radius. And by adding these solar abundances, we now can also constrain the mental composition. But how does the ability to constrain the core radius depends actually on the uncertainty that we have on these abundance ratios? And so I show you for Kepler 36b as well as for Earth 3 times the posterior distribution of the core radius for different uncertainties for these elemental abundances. So we have very small uncertainties of 1%, the actually solar uncertainties, and infinitely large uncertainties on these abundance constraints. And we see that the ability to constrain the core radius doesn't actually increase much or doesn't increase significantly when we reduce the uncertainties of these abundance constraints. Still, in this case, we have very high uncertainties on the mass and the radius. So it might be that here, these uncertainties on mass and radius are the dominant uncertainties. So what happens if we assume very small uncertainties? Here, the picture changes, and we see 2 things. First, the ability to constrain now the core radius increases significantly when we reduce the data uncertainty on these abundance constraints, so when we go from the right to the left. And we also see that we have a difference between the Earth case and the Kepler 36b case. So the ability to constrain the core radius does not only depend on the data uncertainty, but also on the actual mass and density of these planets. So to conclude, given the sparse data that we have, it's still possible to constrain the interior structure. These stellar abundances, iron to silicates, magnesium to silicates, that we can measure from the photosphere of the stars, these are really key parameters to constrain the interiors. And how well we can constrain the interior structure depends on the actual data itself as well as on the data uncertainties. And for the future, we want to increase the complexity by adding oceans and atmospheres. Furthermore, given that there's an uncertainty or associated with the equation of states, we want to include these as well. And there might be constraints for the interior structure that we can use from orbital characteristics as well. And that's it. Thank you.